Okay, this is the second part. Due to the only 10-minute time limit I have, we have to do this in parts here. So, but where we left off was the AlexNet. This is the modern day type of CNN, convolutional neural network. This was invented by Alex Krzyzewski. Probably mispronouncing that, but this is the more modern model of the 2012. Came out in 2012, and this is the one that is used today, but of course it's been varied a lot since then, of course. But this is the one that you can handle a lot more data and information. Has all these max pooling and convolutional layers that we're going to talk about in a minute. Connect to a fully layer, and can be classified. This can handle a lot more data, utilize the GPUs, the parallel processing power, what they call a graphics processing unit, which is the units in the computer that handles graphics processing. And because it has multiple cores rather than just a single core like a CPU, it can handle more data. So designing the CNN. So we're going to cover the convolutional layer, max pooling layer, the flattening layer, and of course the ANN, the fully connected layer. The CNN unfortunately can't do anything with the information by itself. It can't classify it. That's what we have to do. We need an ANN to do the classification for us. So that's what the idea here behind the ANN is for. So that's what we're going to talk about that when we get to it. So now, step one, convolutional layer. We have images, input images like this, 5 by 5 pixels. It could be much bigger than this. This is just a small example of how essentially this is an input image. It could be a car, it could be a bus, it could be a guy on a bike, it could be a bird, whatever it is. It's broken up into pixels here. This feature detector or kernel or filter, there's several different names for it, creates a matrix product operation matrix algebra. It's placed over here. See its shadow image from here to here, and a form what we call dot product matrix multiplication, and it'll come out as a product, which we're going to talk about over here, but just let me walk you through it here. And the main goal of this step is to identify key features in the image. Okay, convolution, by the way, comes from it's an electrical engineering terminology. Computer science kind of stole it, and we use our own, use it for our own um, to explain other things here. But essentially, what we do is this is the layer to extract features. It tries to preserve the relationship between the pixels by learning image features using small squares of input data. Those are called pixels, or key points of light, and it's through mathematical operations. It takes in two inputs, such as a matrix and here, and a filter here, and produces an output here. So if we consider this 5 by 5 pixel image, whose values are between 0 and 1. This doesn't have to be 1, it could be 0.97, it could be 0.25, it could be 0.17. He's just kind of showing the two extremes, 0, which is nothing, and then 1, which is most important. We filter then the image. And then what this does, it creates a feature map, which is going to be shown in the next slide here. But the convolution of an image with different filters can perform different operations, and we can see with different strides is another thing. So the image here, this feature detector filter will go over the image based on certain strides. And all that is, but it is a hyperparameter that you have to, as a designer, have to input. So it could be a stride of 1, stride of 2, stride of 10, depending on. But it's simply the number of pixel shifts it goes over, okay, at a time. Over the input matrix. So for example, the stride of 1, there will be it goes over just one of the pixel images at a time. If there's a stride of 2, then we'll move over two pixels at a time, and so on. The size of the feature detector is a matter. If the image is too big, this feature detector is too big, it can overlook some important features. And if this feature detector is too small, it's going to miss some important features. So it really depends. We're working with, it looks like kind of a small data set of 5 by 5, but maybe the image is much bigger, and we might need a bigger feature map to kind of capture all that information. Padding is another type of parameter that we need to worry about, and this is just to keep the original dimensionality. This is sometimes the filter doesn't have fit perfectly over the input image. I think there's an example in the next slide. And so we have to pad it, quote unquote, with zeros to kind of maintain its dimensionality, so we don't have too much variability of the output by, if this is a 3x3 feature, and then we're multiplying something that's 2x2, it's going to kind of screw with the output, and we don't want to do that too much. So this is our convol feature here. This is our kernel matrix, and like you see here, this is this here, filter matrix here. This goes on top here, as you can see, and it's going over using a stride, say 2x2, and here's these zeros here, right? These are, we're padding it with images, so that doesn't mean anything, but to keep its dimensionality, we want to use this, pad it with zeros. I mean, we could use more zeros, depending on the image and depending on what you're trying to do here, but we really care about these images here. And what we're trying to do is we're doing matrix algebra, and you can see the equation here, 0 times -1 plus, we always use a bias, by the way, 105, which is here, times 5 plus 102 times -1, and essentially one of the products can be, when we output it, can be 320. You can see how, when we automate this thing, it will be much better than to actually do this by hand. So now, when we have the result, we have activation maps. The idea here is that with different filters, we can perform operations such as edge detection. If the image is too blurry, or we can sharpen it by applying filters. We can see here below this example here, various convolutional images after applying different types of filtering or kernels. It kind of goes back to Hubel and the Weasel study before we have the study of, there's simple and complex cells, remember? And how different cells, like simple cells, will just pick out basic images like lines, horizontal lines versus lines that go up and down, versus like the square here looks like there's just white spot, and here's like maybe dark spot, just basic kind of images, right? And these are what we call like low-level feature edges. And then maybe mid-level would be like corners or blobs. It's kind of starting to get some, real images that you can kind of make out like an eye or, a mouth or something. Here's going to be a car, so you can see a tire, maybe a quarter panel. And then high-level, more abstract features, faces, things. And it just gets more complex in terms of detail, and we finally make it to the top here. We have faces. And here we have cars, from this basic, just low-level features. Okay, nothing can't really be discerned from that, to mid-level to and then here we have, these are cars, and these would be different images of cars, right? And here, this was here, and then finally we get, this is elephants, okay? And it looks like there's different pictures of elements too, or elephants, right? Elephants, and so this really takes care of the convolutional layer. What I want to talk to you about now, which I think is important, is the rectified linear unit. This is an activation unit, activation function rather, that is used in artificial neural networks, more specifically in convolutional neural networks, because it increases what we call nonlinearity. Don't say that 10 times fast, of the image. We could use other types of activation functions, but the ReLU function is probably the most effective here. Rectified linear unit increases nonlinearity. Most images in life, okay, out in the real world, are nonlinear. So what all this is that if an input comes in that's negative, the rectified linear unit right here. See if we can look at this. If the image is if the value is 0, which means this is the x plane right here. If this is below this line here, this is the 0 line. If it's below, it's going to knock it up back to 0. Knock it up back to 0. Okay. There are other types of. I'm going to cut off here in a minute. There are other types of a more advanced type of ReLU called the leaky ReLU, which does allow for a little bit of negative value, but for all intents and purposes, we use the ReLU, which doesn't allow for any negativity. We could use hyperbolic tangents and logistic sigmoid functions, but they just don't function as well here. So the next video, we're going to cover more about ReLUs and their effect on our CNN.